All right, today we're tackling what might just be the single most successful scientific theory of all time, the Standard Model of particle physics. Seriously, it's our best guide to the fundamental particles and forces that make up, well, pretty much everything. So let's get into it and break down the blueprint of our reality. To really get the Standard Model, we have to start with the most basic question you can possibly imagine, one that people have been asking for thousands of years.
I mean, really think about it. If you take a piece of matter and just keep breaking it down smaller and smaller and smaller, where do you eventually end up? What is the universe truly made of at the very bottom?
Well, the Standard Model is our best answer so far, and it's an incredibly accurate theory. It describes all the tiny elementary particles that make up matter, and it also describes the forces that tell them how to interact. Specifically, the electromagnetic, the weak, and the strong forces. You'll notice one's missing. Gravity. Yeah, we'll get to that. So who are the main players in this whole cosmic story? The Standard Model basically provides us with a complete cast of characters. You know, probably the easiest way to wrap your head around this is to think of it like a periodic table. But instead of elements like hydrogen or gold, this table organizes the most fundamental particles that we know exist. And here it is, the whole chart. I know, it looks like a lot, right? But don't worry, it's actually pretty simple when you break it down. All known particles fit into two main families. You've got your fermions, those are the matter particles, and you've got your bosons, which are the force particles. And we'll see the bosons have a couple of different types themselves, but let's stick with the two big families for now. So on one side, we have the fermions. This is the stuff of the universe. On the other side are the bosons. They're the ones carrying the forces, kind of laying down the rules for how all the stuff gets to interact.
Let's focus on the fermions first. These are the building blocks. The quarks inside a proton, the electron orbiting an atom, they're all fermions, and they have this one super important rule they have to follow, called the Pauli exclusion principle. All it means is that two identical fermions can't be in the exact same state at the same time. It's why matter is solid. It's why you don't just fall through the floor. It's what makes matter matter.
Now, the fermion family itself is split into two little groups. First up, you've got the quarks. These guys bunch together to form bigger things, like the protons and neutrons in an atom's nucleus. And second, you've got the leptons. The most famous lepton, the celebrity of the group, is the electron, but it also has heavier cousins and these super mysterious lightweight partners called neutrinos. And this is where things get a little weird. See, matter comes in three distinct generations. The first generation, the up quark, the down quark, and the electron, that's our world. That's what makes up all the stable matter you see around you. The second and third generations are basically just heavier, really unstable copies of the first. They only pop into existence in super high-energy places, like a particle collider, and then they disappear almost instantly. And honestly, why nature needed three copies instead of just one is one of the biggest unsolved mysteries in all of physics. Okay, so we've got our matter particles. But how do they talk to each other? How do they know what to do? What forces actually govern their behavior? Well, that brings us to the other side of the chart, the bosons. These are the gauge bosons, and you can think of them as the messengers of the universe. When two particles interact, what they're really doing is exchanging one of these bosons. That little exchange is what we experience as a force. This table lays it all out. First, you have the strong force, carried by the gluon. This thing is ridiculously powerful, but over a tiny, tiny range. It's what glues quarks together inside protons. Then there's the electromagnetic force, carried by the photon. This one governs pretty much all of electricity, magnetism, and light. And finally, the weak force, carried by the W and Z bosons. It's responsible for stuff like radioactive decay, which, by the way, is a huge deal. It's what powers the sun. But there's one more character in our story, a very, very special one, that answers a huge question: where does mass even come from? See, this was a massive puzzle for physicists. The theory was working beautifully, but the math predicted that the force-carrying particles, like those W and Z bosons, should be massless, just like the photon is. But experiments showed they were actually incredibly heavy. So what gives? The theory had a giant hole in it. The answer, which was proposed way back in 1964, was absolutely brilliant. It imagined a new kind of energy field that fills the entire universe, the Higgs field. And associated with this field, there had to be a particle, the Higgs boson. This is that unique scalar boson. It's special because it doesn't carry a force in the usual way.
The key idea is that this Higgs field is everywhere. It's like the entire universe is filled with an invisible cosmic molasses. As particles move through space, they have to wade through it. Some particles, like the photon, don't interact with it at all. They just zip right through, remaining massless. But other particles, like the W and Z bosons, really interact with it. They get stuck, they get dragged down by the molasses. And that resistance to motion is what we perceive as mass. The more a particle interacts, the heavier it is. Now, for almost 50 years, this was just a theory on a blackboard. Finding the Higgs boson became one of the great quests of modern science. It all came to a head in 2012 with the huge experiments at the Large Hadron Collider at CERN. And after sifting through an unbelievable amount of data from trillions and trillions of particle collisions, they found it.
And there it was, a brand new particle with a specific mass, about 133 times heavier than a proton. It was a perfect fit. The final missing piece of the standard model had just clicked into place.
So, with the discovery of the Higgs, the standard model was complete. An incredible scientific triumph. But, like any great map, it also shows you exactly where the edges of your knowledge are. It shows you the uncharted territory.
So, does this mean physics is done? Is this the ultimate theory of everything? The answer to that is a resounding no, not even close. The standard model is amazing, but it has huge blind spots. Gaping holes. First off, it has absolutely no explanation for gravity. And it has nothing to say about dark matter or dark energy, which together make up 95% of the cosmos. It also can't explain why the universe is made of matter instead of an equal amount of antimatter. These are some of the biggest questions in all of science today, and they are completely outside the standard model.
And that leaves us with this final thought, which is just perfect. The standard model isn't the theory of everything. It's the theory of almost everything. It's the rock-solid foundation that all future physics will be built on. A beautiful and powerful guide to the universe we know, and at the same time, a beacon pointing us toward all the vast mysteries we have yet to solve.